Well, first to say how pleased I am to be here again in San Sebastian at the Passion for Knowledge. I've spoken in 3 of them so far, I think. Today I'm not going to speak about invisibility, I'm talking about visibility and how we can see very, very small things, how we can capture light on the nanoscale. Why is this important? Well, it turns out that with ordinary lenses, you can only see things which are of the order of the wavelength of light, which is about half a micron. And Abbe came up with this law a very long time ago when people were making really, really good lenses. They discovered that however well they made them, they couldn't see things smaller than this limit, which Abbe discovered. This is unfortunate because a microscope is a tool of choice of biologists, and it's just running out of resolving power when you're trying to see inside a living cell. And so biologists in particular are very desperate to have techniques which can see smaller than this Abbe limit. It's breaking through this limit that's been a huge challenge for many decades. But it's not only in biology. The electronic circuits inside your cell phone are made on a scale using light, which is much, much finer than the wavelength of light. And very, very clever technology has been developed so that you can actually make things which are much smaller than the wavelength of light. And then there's the question of using light to sense things. Light is a great sensor of various molecules, but it has a big disadvantage because light, the photon, typically is of the size of the wavelength of light, as I explained, but it's trying to see something, a molecule, which is perhaps 1,000 times smaller than that. And it's a conversation between a mouse and an elephant. And if you could squash the photon down to the nanoscale so that it was the same size as the molecule, then it would have a bigger chance of hitting that molecule and detecting it for you. So detection of single molecules is something for which you need to have this nanoscale control of light. And then something else which is peculiar about light is that most particles interact with one another rather strongly. So if you have several electrons in a quantum well, say, then those electrons are very much aware of one another's presence because of the electrical charge. Photons don't have a charge, and by and large, they don't see one another. So I can use this laser pointer, and the light from the pointer will go in a straight line to the screen, even though there are masses of photons coming down from these lights in the theater. They just ignore one another. And that is very useful if you have a laser pointer, but if you want to make switches and make light switch light and make a light computer, then that's not very useful. Sometimes you want photons to see one another. And to see one another, you've got to squash them down to the nanoscale and make a very, very powerful concentration of energy there. And then sometimes they can see one another. And then there are all sorts of exotica you want to go into. It's possible, actually, to time reverse light. So you can take light coming from an object and use special screens to send it right back to the place where it came from. But current technology requires high powers, so most people aren't aware and don't use this technology because it's so expensive. So that's the motivation for looking at light on the nanoscale. And to explain how we do it, I want to go through some background, to go through some history about how people have understood light in the past, how we've come to a modern understanding of light, and how that modern understanding can also give us control of light on an unprecedented length scale. Some of you will have heard of Snell's law. Snell wasn't the only person to think of this law. Descartes also thought of it, so if you're French, you'll call it Descartes' law. Newton quoted it in his optics book without acknowledgement. Whether he invented it himself or not, I don't know, but Newton was that sort of man anyway. And what this tells us is that the way light changes direction at a surface here depends on something called the refractive power of the medium. And it's a constant for each different medium through which light can pass, glass, water, and so on. And the refractive index is a measure of how strongly this light is refracted at the surface. And this mathematical formula tells you how to design lenses and whatnot. Now, you might say that that formula is completely out of date. It's hundreds of years old, and since it was announced, people have understood light in a different way. Snell thought of light as a stream of particles, and now we know that, although we think of photons, that light is also a wave. And it has, in addition to being a wave, it has a polarization. And also, the light, not all of the light goes through here. You're aware that some of the light will be reflected. None of this is contained in Snell's law, and yet it's still used as a design tool. And the reason for that is that it gives such an intuitive feel of how light will behave when it interacts with matter, that we use it as a thinking tool, as a creative tool, and so it's still in existence and used hundreds of years after it was founded, and decades after it's been proved to be not very accurate. Now, somebody who was very instrumental in the development of optical instruments was Galileo. And we heard about Galileo in the lectures last night. He didn't invent the telescope, but he certainly made the best telescopes around at the time, which were capable of doing really serious astronomical work, such as discovering the moons of Jupiter. And this concept of a lens which can focus light and so make an image, you can look at stars through a telescope, has been the standard model of how we focus light and use it for many years. By the way, I don't know how many of you know where the word lens comes from. It comes from this little bean here, a lentil. And you can see from this photograph I've taken that the lenticular shape is similar to that of the lens, and that's where the word lens comes from. So on to more modern times, not all that modern, but in about 1860-something, a man called Maxwell made a great discovery about light. People have been using light and controlling it using Snell's law and grinding lenses, but they never knew what light was. What does light consist of? And what Maxwell showed when he was investigating electricity and magnetism, he showed that actually electricity and magnetism make light. And he wrote down these equations here, and I know some of you are not mathematicians, but they're so famous that I have to show them. They're Maxwell's equations. And what he showed was that if you have a magnetic field that changes with time, then that creates an electric field. And if you have an electric field which changes with time, that creates a magnetic field. And he mentioned this to Lord Kelvin, and Kelvin said, well, that looks like a potential for a wave. And Maxwell, being a brilliant mathematician, soon found his wave, and he calculated the speed of that wave. And it turned out to be the known speed of light. And so it was that Maxwell discovered the ingredients of light, that light is a dance. It's a dance between an electric field turning into a magnetic field, and in turn turning back into an electric field. The step of the dance, the distance it takes to make that transition, is the wavelength, and the time it takes is the beat of the dance. So light is a dance between electric and magnetic fields. And we'll have to use that fact in order to understand how to control light on a much finer scale than we have done so far. Now, with that discovery, Maxwell created a great controversy, because up until that time, when people had thought of waves, it was always a wave in something. So when we hear a sound, it's a disturbance of the air, a wave of the air. If you look outside on the sea, it will have waves, and that's a water wave, it's water moving. But when you have a wave moving through vacuum, what is moving? And that was a great philosophical puzzle at the time, because a vacuum, empty space, was, people sort of ran out of words to describe the emptiness of space. Nothing, vacuum, emptiness. And yet, this emptiness supports these waves, these electromagnetic waves. It supports light. And people invented names for it, the luminiferous ether. And they asked the question, is this medium, this ether through which the light propagates, stationary, or is it moving? Or are we moving relative to it? And when the Earth goes round the sun, do we move at different speeds through this ether? And that question was resolved by this man, because he said that the vacuum is not an empty thing. It's another material, just like glass or water. Space is a material with properties. And the property of space is its geometry. And living on Earth and in a relatively modest gravitational field, the geometry of space is a constant for us. We take it for granted. But you can change the geometry of space. And when Einstein came up with his general theory, he showed that, according to his theory, if you have a very massive gravitational object, and the sun isn't all that massive, but it's a lot more massive than the Earth, then it's capable of bending light. And when Einstein produced his magical equations of general relativity, one of the first things he did was to see how Maxwell's equations looked when he rewrote them in terms of his general relativity equations. Maxwell was a great hero of Einstein. Maxwell's portrait hung above his fireplace in Princeton. So much did he admire the man. And when he asked, how does his properties of space look in Maxwell's equations? Well, first I should tell you how he described space. He described the geometry of space in terms of something he called the metric. And the metric simply says how much the gravitational field squashes or stretches or pulls space. And this quantity, the metric, when he rewrote Maxwell's equation, appears in Maxwell's equations in exactly the same space as does this quantity, the refractive index, which I mentioned earlier. So as far as light is concerned, you can either bend it around using a refractive index, or if you're very high-minded, you can use the sun to bend it, or a black hole, or something very massive. And in fact, this experiment, as I explained to us last night, was one of the foundation stones of general relativity, this prediction that the sun should bend light so that a star being eclipsed by the sun actually appears in a different place in the heavens from where conventional astronomy would have it. That observation by Eddington was the foundation, confirmed the foundation of general relativity. And we're going to take hold of this concept of the geometry of space and the metric, because when you bend space, you take the light with it, as we see here. So the sun is bending space, and the bent space takes hold of the beam of light and it too is bent along with it. And we can either do that by bending space, or we can do it by changing the refractive index. Here's another example of something really, really massive bending light. Here we have a very massive red galaxy in the foreground here, and behind it is a blue galaxy, and the light, instead of being stopped by this galaxy here, is in fact bent around it here, and you see this ring, which is gravitational lensing in play. So it's a very real effect. Well, back to more earthly things. You're familiar with this concept of refraction by now, I think. But what about if there was a different sort of refraction? And a man called Veselago discussed that quite a number of years ago, in 1968, I think. And he asked the question, what would happen if you took light into a medium which, instead of bending the light this side of the normal to the surface, actually bent it this side here? And to do that, you need something with a refractive index, if you believe Snell's law. And he worked through the consequences of things with a negative refractive index. And I'll tell you some of the very strange qualities that he found. First of all, this is what, if you send a pulse of light in here, then because of the negative refraction, the light will follow this trajectory here. But there's another very important law. So this vector is the velocity of the light. As it changes, the velocity changes its direction. This vector here I've drawn is how the wave of which the light consists is propagating, and that's the direction the wave travels. I'll explain the difference in a moment. And there's a very strict symmetry law which says if there's a flat surface here, the projection of this wave vector must be conserved. And so you have to come to the conclusion that the direction of propagation of the light and the direction of a pulse of light and the direction of propagation of the waves are in opposite direction. I try to explain that a little better here with this picture. So I'm making a pulse of light, and here are the oscillations of the electric and magnetic fields, and this is what we call the group velocity. The envelope goes this way. But if you peer inside the envelope, you see that the waves are actually going in the other direction here. And that's the signature tune of this weird thing which Veselago thought of many years ago, of negative refraction. And something else that he realized was that because you get this folding back of the light on itself, you can actually make a new sort of lens, the Veselago lens. So if you have a point source of light here, you get a focus here, and then you get another go at the focus here. It comes to two foci after the original illumination. And that's a very strange sort of lens, because although we might call it a lens, it is not lenticular in shape. It's just a slab of material. But still, it can focus because of this weird property of negative refraction. Now, another strange thing it can do is this. So imagine you had a swimming pool or a goldfish pond, in this case, full of a medium which actually had a negative refractive index. And if you do this ray tracing thing, you'll see that actually the fish down here would have an image up here. So it would be rather a nice pond because you'd see your fish swimming around in free space. Very, very curious series of things. And they all follow from this apparently trivial statement that you can have a negative refractive index. Actually, there's something even more strange about that negative refractive index, because I've explained this lens in terms of Snell's law, but there's another way of explaining this lens, which is why I've been so careful to drag Einstein into the picture. So I'm going to exploit this analogy between a refractive index, which bends light, and a gravitational field which changes the metric of space, squashes space, and also bends light. And they do the same thing. And so I'm going to create some negative refracting material by squashing space. And here's my experiment. I'm going to squash this bit of space in between. And as I squash it, the metric increases, and the equivalent refractive index increases, and I squash it more and more. And if I squash it infinitely hard, you get an infinite metric, an infinite refractive index, and then I squash it some more. I turn it in on itself. You know that if you make something go to infinity, on the other side it comes out minus infinity. Well, that's exactly what happens here. So I made a bit of negative space, and you can see what it's doing because it's folding space and it's cancelling out the bits of space either side, and it's negative. But there's something else that's weird about this. So I started off with regular flat space, and I squashed it a bit, and nothing very exciting happened. But now the space has a completely different property. So when I'm here, I'm also here and here. So I made a space which has three surfaces, or manifolds in the technical term. And that is a result which is exact at the level of Maxwell's equations as reinterpreted by Einstein. So what we think the light is doing is going through like this, positive, negative, positive, but what the light thinks it's doing is doubling back on itself. So as it retraces its steps, it has been focused here, it comes to a focus a second time directly under this bit of the manifold, and as it passes out through the positive bit again, it encounters itself again. So there are three doubles here. There are three copies of the thing in this peculiar sort of space. Now, since that result was derived not with the approximate Snell's law, but with the exact Maxwell's equations, the statement that it comes to a focus is no longer an imprecise one. It's an exact one. And so, as I showed a number of years ago, if you make a lens which has exactly these quantities here, a negative refractive index of exactly -1, and you must do it perfectly, then you will have made a perfect lens that can see anything, no matter how small it is. The catch, of course, is that it's very, very difficult to do that. Veselago didn't realize the perfection of his lens, and he was never able to make one because there was a missing ingredient that never occurs in natural materials. And it was only until we came up with the idea of the concept of metamaterials that we're able to make materials with a negative refractive index, and that could go some way, not all the way, to making a perfect lens. And so that brings me, finally, to the subject of my talk. You have to make something with a negative refractive index, but light has two components, so you've got to do that thing for both the electric and the magnetic field. So both the electrical response and the magnetic response have to be negative. And the electrical one is okay for light-type waves, but the magnetic one is nearly impossible. Not completely, but almost impossible. Very difficult to do that one. So instead, you can do what I call the poor man's superlens. And the argument looks like this, that I explained to you about the dance of light. So you start off, say, with an electric field emitted by a molecule which is reacting in some way. And as that light goes further, the electric field turns into a magnetic field. But it has to take some time, and also, importantly, a distance of about 0.5 micron to do that, and that's a long way. And if you want to see things which are very small, much less than half a micron, and which are not far away from one another by more than half a micron, then that electric field never has a chance to turn into a magnetic field. And so you don't care what the magnetic response is. So if you want to see really, really tiny things with a really tiny lens, you only have to bother about the electric field. And you can do that. And it turns out that, strangely enough, we can use silver as a lens. Now, you normally think of silver as a metal through which light does not pass. But on the nanoscale, that's not true. And here is a realization of that poor man's lens made by Zhang Zhang's group. Nick Fand actually did all the hard work with that, and now at MIT. And here's the lens. So here's this slab of silver, which is going to be our Veselago lens. Here's the thing we're trying to see, which is a finely written grating, and the word nano written in chromium. And here's a spacer layer. And of course, if you want to see it focusing, you don't sort of look at it with a microscope. But what you can do is to write the image in a photoresist, develop the photoresist, and then look at it afterwards. And that's what they did. So the light coming in has a wavelength of 365 nanometers. So you shouldn't be able to see anything much smaller than that. But when they did this experiment and asked if they could resolve the grating, you can in fact resolve details which are a sixth of the wavelength of light, and more recent experiments have gone down to, I think, about a twelfth of the wavelength of light. More impactful is this word nano. Here's an image of a focused ion beam image of the chromium plate. Here's what the photoresist shows, and here's what you see if you don't have any Veselago lens there. So between here and here, here's a scan through one of the letters, and you see how much sharper it is. It's like popping your specs on. Well, for those who wear specs. Well, you may say this lens has the potential to be perfect, but when you think about it, it's a very boring lens. Of course, usually what you want to do with a lens is to see something that's very small and make it appear very big. And that's not what the lens does. It says, no, I'm a perfect lens, so the object and the image are going to be perfectly the same. They're going to be the same size. Well, we can change that, can't we? Because we all know that space, by now, that space is like plastic. You can pull it around and stretch it, providing you have a strong gravitational field. And you can imagine then pulling around the space around this negative refractive index material and shaping it into, instead of being a flat slab, shaping it into an annulus. So one side of the slab becomes the interior of this sphere, of this annulus rather, and the other side of the slab becomes the exterior. And now, because you stretch space here and squashed it here, objects inside here are projected onto this red ring here in a magnified form. And you can do your mathematics and come up with a formula for this lens, and lenses like this have been made. But there are some things I want to show you which might be rather surprising. So here is a computer simulation. I did have actually, let's see, no, I won't do it. There's an animation here, but it didn't work when we tested things, so I won't do it. Here's a computer simulation which says that anything inside here, in this case a set of waves, is reproduced outside this region in a magnified form. And this is a computer simulation which shows that that's exactly so. So the spacing here is much larger than the spacing here, and here's the lens doing its business in between. Now, let's look at this from the point of view of Snell's law. And this shows you how Snell's law completely fails to describe this situation. I can say, well, here's a ray, and that one goes straight through because it's instant normal. This ray hits the surface, and a negative refraction here, negative refraction there, and on the way out, so that's fine. This is the last guy to actually hit the lens, and he goes in here. But what about all this stuff up here, which the computer simulation shows is really there, but these rays, how do they get inside here? Because they're supposed to be in the top half of this thing, but there's no way that they can physically, in terms of Snell's law, hit that lens and get in there. So to just show you how weird it is, I use this analogy with, it's better with a bottle of milk, but I have water here. I don't know if you've ever noticed when you've looked at a bottle of milk, a glass bottle of milk, the milk goes right to the edge of the glass. Even though you know that the glass is thick, you see the milk right to the edge. And that's very easy to explain, because if you use Snell's law, you can show that if light hits the glass, wherever it hits it, it's also got to go in some milk. So the light will always be milk-colored wherever it comes from on that circumference. But this bottle is different. What it says is that if you have some light going past here, that also will hit the milk. So this bottle of milk, which looks like water, the milk would actually appear to be here, a bit like that funny goldfish in that pond that leapt out of the pond. That's really weird. It's something you just cannot understand in terms of Snell's law, and for which you need this more advanced theory in terms of Einstein's distortion of space. Well, I've been talking about some of the exotic things that you can do. Oh, here's one more. Sorry, yes. Okay. Now, it's difficult to make a shadow of nano objects. It's due to the diffraction of light. So if you take a situation like this here, you see that the light, although it hits something black here, is actually filling in the region behind, and that's due to diffraction. And what I want to do here is to use this funny lens to make a shadow which is much bigger than the object producing it. So I start with something which is black and very small, and then I wrap this lens around it, and if you believe my figure here, then anything that comes in here will be dragged into this black region in the middle here. And so you can see in this computer simulation that waves hitting this object here, even though the only physical thing is this blue guy here, and the black material inside it, that it can produce this huge shadow for something very, very small, which is kind of fun. So let's get a little serious here. Can we really, really focus light down to a nanometer? And the answer is yes. And to understand it, how we can do that, I turn to this geometry thing here. So what I've got here is a source of light. This might be an atom emitting some light. And it's in a waveguide, and it's going to capture this light, and the waves are going to go down the waveguide to infinity here. That's a very well understood device of light propagating in a waveguide. But I'm not content with that. I'm going to say, I don't want the light to go to infinity. I want it to go down to a nanometer. So I'm going to crush that waveguide, turn it inside out, and this top half is going to make one cylinder, and this bottom half is going to make another cylinder here. And what's more, this point here, I brought it from infinity. So these waves now, which started their life here, that bit comes from there. Can you imagine my pulling it around like that? And they, instead of going sort of to infinity, infinity is now this point here, and they coalesce at this point here. And if all works well, because here they go with a constant velocity, but because they've been squashed, they're going slower and slower. And if you think about cars on a motorway going slower and slower, they get closer together, their density gets higher, and so the energy density increases enormously here. Or should do, but does it? Well, here's a computer simulation. I'll show you some experiments in a moment. And this shows that there's some light coming in from here. These bits are grabbing the light, and they're shoving the light into this point where the spheres touch, or almost touch. And there should be a very, very high concentration of energy there. That figure doesn't show the concentration very well, but here's a plot of the strength of the electric field as you go round in angle from 0 degrees to 180 degrees, which is where the focusing takes place. And you can see that nothing much happens until you really start swashing the light. The wavelength decreases enormously, and it builds up to 1,000 times, more than 1,000 times the intensity of the incident light. The effect eventually stops. It would go to infinity, but there are some losses in this system, and when the wave goes slowly, it's very susceptible to loss. So eventually, this effect collapses, and at the touching point, you don't get anything, but on the way, you get this very huge enhancement. And the distances, by the way, I should say, draw your attention to the fact that this is 40 nanometers across, and this is less than a nanometer, this region over which you're doing the focusing. So theoretically and computationally, you should be able to do this. I had another video, but it doesn't work. So let's move on to the experiment. These are experiments done in David Smith's lab in Duke University, and they take the key to it is to have two surfaces which touch one another, and almost any two will do, provided they're made of something like gold or silver. And to ensure their perfectly well-known separation, he has a layer of molecules here of known size. So there's a gold film, a nanoparticle 60 nanometers in diameter, and he's going to shine some light on this and measure the increase in intensity of the light at that point. And the way he's going to do that is to put some molecules here which scatter the light, and he's going to measure the signal from those molecules. It's called the Raman spectrum, but you don't need to know that. All that you need to know is that they give you a signal which is related to the intensity of the light here. So there's the setup, and here is what David Smith's team measures. So as the distance between this distance here between the sphere and the gold film decreases, the enhancement effect gets greater and greater, and eventually you get this 10 to the 4th enhancement here. And this gives you the potential for single molecule sensing, is known as a giant Raman effect. So I've taken you on a journey through history, through some theory, through some modern theory, some wild ideas about negative refraction, and finally, these ideas are coming into practice, and the answer is, yes, we can control light on the nanoscale. Thank you for your attention.